Foundations of Programming Counting. We've been talking about base 10, base 8 and base 16 numbers. This short tutorial will help explain what base 8 and base 16 and base 10 numbers are and the significance of base 8 and base 16 in computer programming. And we'll learn how to represent these numbers using a sequence of bits. In counting, our everyday counting, we use what is called base 10. Base 10, we use the digits 0 through 9 to represent our numbers. So when we count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, we move on to the next 10, 11, and so on. That's base 10, using the digits 0 through 9 to represent the numbers that we count with. There's also other bases, and there are actually three bases that are relevant to programming: base 2, base 8, and base 16. Base 2 is binary. Base 8 is octal, and base 16 is hex. We're going to focus on 8 and 16. But firstly, how do we represent a base 10 number using bits? So let's assume that we have 8 bits, as we have in our diagram here. And we have a least significant bit and a most significant bit. So our least significant bit means it has the least value. So what we do is we put a 1 in our least significant bit, and we continue to double the values in each subsequent bit . 128. So if we wanted to represent the number 140 in base 10 using bits, so this is just our normal 140 that we count with. 140, we need 128, which leaves us 12 more, which would be 128, and we would need 100 plus 8 is 136, plus 4 is 140. So we just fill the rest up with zeros. And that's how we end up with our number 140. 128 plus 8 is 136 plus 4. So 128 plus 8 is 136 plus 4 is 140. So we've represented the number 140 using a sequence of bits. Remember, the least significant bit in these examples is on our right, and the most significant bit is on our left. Now let's look at an example of base 8. Now base 8 is using the digits 0 through 7 to represent our numbers. So it'll be 0, 1, 2, 3, 4, 5, 6, 7. Now in base 10 we would go 8, but here, because we're talking base 8, we go 10, 11, 12, 13, 14, 15, 16, 17, 20, 21, and so forth. The important thing is that each of these numbers is represented by the digits 0 through 7. And it just so happens in base 8 we need 3 bits to represent one digit in base 8. Let's see what we mean. So base 8, as we said, is octal. We have our least significant bit on our right and our most significant bit on our left. So again, we're going to group in threes. and our least significant bit we put a 1, double to 4. Now, because base 8 is 3 numbers, 1 plus 2 plus 4 is 7, so that's the maximum we can have. Again, 1, 2, 4, another 7, 1, 2. Now there's no ninth bit, so we just put a 0 in there and pretend it's a 0. Fixed at 0. So, if we want to represent an octal number, for example, let's say we wanted to represent 216 in octal as 216 octal. The first digit we have is a 6, so we need a 2 and a 4. Gives us 6. The next digit we would need is a 1. So fill that up with zeros. And the next digit we need is a 2, which corresponds to that 2 there. So there's 216 in octal. Of course, if we wanted to get the decimal representation of that, of 216, we would go back into decimal mode, and we would see that 216 octal is equivalent to 128 plus 8 plus 4 plus 2, which 136 plus 4 is 142 decimal. I know this may be a little confusing, but bear with me. So let's run through that example again of how we convert a octal number to a decimal. Let's choose the number 156 octal. So 156 octal. Remember 1, 2, 4, 1, 2, 4, 1, 2. Because this is octal, we need 6, which is a 4 and a 2, a 5, which is a 4 and a 1, and a 1. We put zeros everywhere else. Now, what's this representation in decimal? It's 1, 2, 4, 8, 16, 32, 64, 128. So we have, let's write this number out again. We have 64 plus 32 plus 8 plus 4 plus 2. And that equals 96 plus 8 is 104 plus 6 is 110 decimal. So that's how we represent numbers in octal and how we convert numbers from octal to decimal. So an octal is 3 bits to represent 1 digit. Base 16 is a little bit different again. Same principle, but rather than using 3 bits to represent, we use 4 bits. And we're using the digits 0 through 15 to represent our numbers. Now, counting in base 16, the question is, how do we represent numbers greater than 9? Three, 4, 5, 6, 7, 8, 9. Now we go A, B, C, D, E. So A corresponds to 10, B corresponds to 11, C to 12, D to 13, E to 14, and F to 15. So that's base 16. So a base 16 number of, say, 2E is essentially 2 and 15. A little bit confusing. We represent hex usually with a 0x2e. This little thing here represents hex. So I need 4 bits to represent a hex number. So let's go and do that. Here's a hex set of 8 bits. And so we need 4 bits. So we simply split our byte down the middle, and it gives us our 4 bits. Least significant bit on the right, most significant bit on the left. 1, 2, 4, 8. 1, 2, 4, 8. So to represent 5F in hex, we simply go, what do I need for a 5 on our most significant hex value? Need a 1 and a 4, zeros everyone else. And for F, we need 15, which is all that filled up. So what is 5x in binary? Well, again, similar story to octal. We go 1, 2, 4, 8, 16, 32, 64, 128. We have 64, anywhere there's a 1 plus 16 plus 8 plus 4 plus 2 plus 1. And what does that come to? 64 plus 16 is 80, plus 10, 90, 95 in base 10, or the numbers that we count with. So let's just finish off just by summarising. We have base 10, which is what we count in. Base 8 uses the digits 0 through 7, and we need 3 bits to represent each digit in a base 8 number. Base 16, which is 0 to 15, and we need 4 bits to represent each digit in a base 16 number. And further, in base 16, the actual digits are represented through 0, 1, 2, 3, 4, 6, 7, 8, 9. 10 is A, B, C, D, E, F. I've hoped you enjoyed this short tutorial on counting and bases, and thank you for paying attention.